language models that we talked about in the workshop previous to this. I was wondering a little bit because you were giving a little a sort of YouTube video where you said what you were going to talk about, and I saw two fuzzy animals in the background. The Go Gophers. Wow, what's that?
It's the mascot, the official mascot of Go, the Golang, the
Cool.
programming language.
All right. Cool. And I also saw them on your LinkedIn profile because you already gave a talk at DEA a little while ago.
I sadly don't have them with me. I usually keep them, like they go with me to meetups and stuff, but not today.
So then during the talk, let's imagine the Go Gophers that they are here. And I'd like, a warm welcome for Jeroen Rissema and his talk.
Yeah, thank you. No, I will not be talking about AI or large language models. Sadly enough, we'll talk about something slightly different. It has something to do with languages, but more about building and writing your own programming language, or the various other ways and things that you could do with it. So, hi, I'm Jeroen Rissema, as just was said. I'm the CTO and co-founder of CloudProud, a startup in Zwolle, where we are trying to build, or where we are building, a decentralized data platform, allowing our customers to connect all of their data sources together without copying it to a centralized location. That's when we started with this startup. We were coming from a large or long data background. We were doing a lot of consulting projects already for quite some time, and we were constantly being fed up and frustrated with how the day-to-day situation is. Because right now, on a day-to-day basis, this is a little bit on how our data landscape is looking like. It's complex, it's messy. There are a lot of moving components, a lot of moving parts. And we have data sources on the left, but then we have to integrate them, we have to store them, transform them, monitor them, version, and in the end we use them somewhere or somehow. And these two places, the data sources and data uses, is actually the only thing we want to care about. So we decided to do something about it, and that's how SceneKit was born. And to tie this a little bit back to my talk, why this is relevant to what I'm going to talk about today is we were essentially decided to start building a database technology from the ground up, with the only difference, we don't have a storage layer. Our data, the data that we are retrieving, comes from the underlying data sources, but our data users can interact with us like it is a database using SQL. So that meant that we had to build a SQL server from the ground up, a SQL engine from the ground up, reverse engineer the Postgres protocol, and allow users to start using it in ways they are already familiar with. Yeah, of course. Yeah, of course. Sorry, this should not touch my cheek, I guess. Yeah. Is it better? Yeah? Perfect. Okay, so the Postgres Wire protocol itself is open source and available for you to use and download and play with. It's actually pretty cool. It allows you to build an entire Postgres server in just 15 lines of code. In Go, of course, because our whole startup is built around Go. So feel free to check it out. This talk will actually dive a little bit deeper in the SQL queries that are coming in and what you can do with them, or how you can build a programming language to allow your users to interact with your solutions in a kind of new or interactive, innovative way. So if we look at a programming language, and especially its compiler, from a high-level overview, it's actually pretty simple. There are 3 steps involved. We have Alexa, which converts texts into tokens. Those tokens are afterwards given to a parser, and that parser interprets the tokens and creates then very often a syntax tree. And that syntax tree is then evaluated, and we create some sort of behavior. And why I say behavior is because not every language that is out there, every programming language, results in the same behavior. Some programming language compile back to machine code or to some other language, say, for example, maybe not the best example, say TypeScript. TypeScript is actually compiling back or transpiling back to JavaScript. Or the behavior can be that you perform an action or that you defined a state or configuration, say, for example, in the case of Docker or other various solutions that are like that out there. If we look at modern solutions, they are slightly more complex. There are a lot more steps involved, a lot more moving components to give the user feedback and the experience that they're used to. I'm going to skip most of them today because you could build already your own one without most of these components. Just with those three that I've shown before, you can already get pretty far. Start with the first step. So what's a lexer? If we have a statement, say we have a constant that where the variable x has a value of 3, and we are logging x, the lexer will split this statement into those parts below. Those parts then are then after coming into nice consumable chunks that are ready to be parsed or to be interpreted, so that we can go to the next step. To do or to build a parser, there are various algorithms and strategies out there. You can go top down, bottom up, left, right, whatever. There are various advantages and disadvantages to those various lexing algorithms. For now, I'm going to keep it very nice and simple. We're going left to right. So as you just saw before, we start with a constant, then we just get the x equals, etc., etc. What comes out of that is the next step, what we want to kind of achieve or create is an abstract syntax tree. An abstract syntax tree represents those tokens in a format where the relation between the components is kind of known. So say we have the statement, if A equals B, then return else of equal, else return A plus not equal to plus B. Then the abstract syntax tree will look a little bit like this, where we have a statement. That's kind of your entry point. All code will start with a statement. Then we have a branch that has a condition, that has an if body and an else body. And within the condition, we have variables and constants and comparisons that we are evaluating or that we want to be evaluated at some point. The nice thing with all of this, what I just shown, is it looks pretty complex and pretty daunting. But there are a lot of solutions and a lot of tools out there that can help you build a lexer, a parser from the ground up in kind of an alternative programming language or in an alternative definition. I just put up a few names here on the screen. So we have FlexYax, Bison, Lemon. Again, all with their benefits and slight alterations and different views and perspectives on what you could do with it with them. But for this talk, I will keep myself focused on Yacc, yet another compiler. Also a little bit to and Yacc, or at least the grammar definitions of Yacc, they are quite commonly used. So for the programming languages and tools that you see here on the screen, not all of them are actively using them right now, but they have been using them either in the past, or there are implementations for these languages in Yacc, allowing you to create or to interpret the code that is coming in to generate that abstract syntax tree. And a Yacc definition looks a little bit like this. So to not make this demo not make this talk very dull and me just talking for an hour, I will dive soon actually some demos, and we will build actually a few languages together. But we, in this case, it's Go Yacc, so it's the Go implementation of Yacc. We can write code, Go code, regular Go code on the top. We can define our union. Our union is actually passed around through our Yacc definition that allows us to store or write values back into some sort of a common state. And then below, we define our tokens and our conditions, where we are literally defining the grammar. So we say, okay, we have an expression. The expression can be a number or an identifier, or it can be an expression on the left side plus an expression on the right side. This application is a simple calculator. thus, therefore, these conditions. But the nice thing is because of this simple definition, and since we are defining that an expression can be on the left or right side, we can create a number of complex scenarios that will be parsed or interpreted by this language. So we can say we can put a letter on the left side, and we can put another expression on the right side that then results in, say, you using some curly brackets to encapsulate a formula. So to summarize it a little bit, we have our lexer, making tokens, parser, interpreting those tokens, that there is a syntax tree, and then we do something with it. Now, the behavior, to go a little bit deeper into that topic, what we can expect. We can write machine code. We can literally write CPU instructions, allowing us to give you a binary that you can just execute and run without any dependencies. We can create an intermediate language. This is actually the case for most programming languages. So say, for example, C#, you've got the intermediate language, the bytecode, that is that's being run on the runtime engine. And as long as you have a runtime engine that is running on any machine, your code will execute. You can trigger an action. So in our case, for example, you can retrieve data through our solution, or represent state, the Docker example. So the demos I will be giving, I hinted already a few times, I will be giving them in Go. Don't worry about it. Go is a C-like syntax. So as long as you've worked with C-like syntaxes before, this will feel pretty natural. We'll use very little dependencies. The only one that kind of is special about this case is Go Yacc. But say if you're looking at a C# or C++ or C implementation of Yacc, they will be pretty familiar. And all code demos are available on this link. So say you want to just play around with them after this talk, feel free to download them, compile them, and just play around, tweak some values, etc., etc. So let's dive into the demo. I hope I prayed enough to the demo gods that these demos worked. I heard already on the beginning of the night that you like some sort of a demo horror story. Let's not hope that it will happen today. But I got here a basic environment. So what I will be doing is on my computer here, we'll be programming, and you guys can hopefully follow along what's going on here on the screen in the middle. So basically, let's start with just making a calculator. Let's make a Yacc definition by making the parser.y. And like I just showed in the example, every Yacc definition starts with sort of an opening statement. I don't know exactly the technical definition of this part, but essentially here on the top, I can write any code that I want to be included. These can be functions, these can be variables, it can be helper methods, whatever you're trying to achieve, you can be throwing it here on the top. Then the next thing we need to define is our union. Union is kind of a funny little thing. It represents the state of our finite state machine. So essentially, Yacc is a form of finite state machine, meaning that you can, it follows a set of instructions, and as long as the instructions are the same, it results in some, not the same, but those instructions result in some state. And the union in our case, in the case of a calculator, means that we have a value, which means that the value will contain the tokens from that are being given from the lexer, and the number will be the end result, the result of the calculator, and that will in the end be given back to the user. The next thing we need to do is we need to identify our tokens. And with these tokens, we sort of define the instruction set that we can expect from our lexer. So in case of a calculator, where we want to be able to store variables, where we want to be able to do things like say, hey, a equals 3, and then a plus 2 results then in 5. Since we want to be able to do these things, we can define now, okay, we have integers, we have numbers, And we have identifiers. In this case, those are the variables, because essentially only this little bit, the letter A that represents the variable, is the thing that we are interested in. We are just, as long as you encounter an A, we want to be aware of it. So let's remove this for now. The next thing that we kind of need, actually, can I not? It will. The next thing we need is we need to define the statements. So we have always some sort of a start statement. Say in case of this calculator, we just call it start. Say in case of a programming language, you can call it actually whatever, it doesn't really matter. And we define, or we start with what you, with kind of the types of blocks that we can encounter. Say in this case, it can be either an expression or an assignment. You cannot combine the two. So if you start an expression, you cannot all of a sudden go to an assignment. That is the limitation in this case of Go YAC and the way on how we're lexing. We cannot go back and forth. Say it allows us, but it's quite simple to define then these definitions this way, because we can just combine the two and go from one to the other. Within the expression statement, now I went already a little bit in deeper into it before, but it essentially means all the possible combinations that we can create. So you have there plus, minus, multiplications, divide by, or say you want to use some curly brackets. Or, and that's quite important, negative integers, because that can be be a valid use case as well. And next, what we actually need to do is we just have to take this and build a lexer for it. So this lexer, is a separate program that we'll be writing. So let's call it package main. And let me copy at least a little bit of code from here. To start with, the lexer struct will look a little bit like this, where we have want to keep track of our position. We have some sort of an input string. We want to be able to handle some sort of a variable, and to kind of keep our state while the application is running. We want to be able to store the variables that are coming in one way or another. The lexer itself looks a little bit more as following, where we have our lexer function, actually that is being triggered every time we are running the program, where we are grabbing our position. And while we are in the lexer, that's the moment when we are trying to figure out, okay, what is it we are looking at right now? So we have a raw piece of string, some raw code. How am I going to interpret this? So if it's a space, I want to just ignore it, because spaces are just pointless to me. If it's a number, then I simply want to say, oh, hey, now then this key, this token is a number, indicating to our parser, like, okay, hey, I can handle it as a number, so thus I have to follow the different paths and ways in the YAC statement that I've made. If it's a letter, then it's an identifier, and after the switch case is done, or if it's none of the things above, just increment my position and continue. So I have to copy a little bit of boilerplate code in. So because we want to, oh, why is it not scrolling with me anymore? That's funny. There we go. Work again? Yeah, perfect. So we want to be able to handle errors. And I want to add a little bit of boilerplate code on the top to be able to kind of give a usable interface where I soon can put in the formulas. But as you just, before we can go there, we have to kind of expand this definition a little bit. Because right now we are not really indicating to the parser what to do at all with the values or the expressions that are coming in. So to do that, we can add code blocks to the definition. So I can add with curly brackets at the end of the line an expression allowing me to define the logic or the code that has to be generated to be put into place. Say in case of a number, say we're here within the expression, the code block will look a little bit more like this. So hey, we have then a number token has been identified. So in this case, now since that it's in string that is coming in, we want to parse it to a float and then return it back with these double dollars to that state that we have defined above. And with the identifier, it's pretty similar as well. So actually, let me copy the remainings so that all of this is now in place. And by defining these code blocks, we can kind of define all the behavior that we want to be put into place. And here you also will see now in Go code, then I will generate in the end. Okay, say I have two expressions in this case on the left and on the right side. I then want to do the first expression plus the third expression because the plus token in this case is also being counted and taken into account. And that is then my expected outcome. The next step is that I need to expand the program a little bit more. 1 second. Of course, during a demo, that's the moment when it doesn't work. A little bit more, just to finalize it, I have to just define my constants. So we've been using those plus and minuses before, and I just want I need to include them in YAC code as well to make them work. But in the end, if everything works together, let's see. If I build it, then it doesn't work because I have to download the dependencies. And it still doesn't work. So let's just download next, which apparently didn't do. And Go YAC it didn't download. Sweet. And oh, it of course is downloading my demo. So open Lexer. Oh, nice. I swapped around my build pipelines. 1 sec. This is indeed, yeah, sweating, eh? Like, no, it's not. Yeah. Trust me, like it's better to just sit there. So let's see if it works. Yeah, it worked. So I just swapped around my build pipeline of my build shell scripts or bash scripts around, which is not really a great thing to do. And once it compiles, actually, what you end up with is this gigantic file. And this is the reason why it's really nice. Oh, actually, this one is not even that big. But this is really the reason why it's nice to have a tool like a parser, because this finite state machine handles all those scenarios we just discussed. All those possible iterations, all those possible combinations, this state machine is just handling it for you as long as you feed it with the right tokens. It's still complaining. Oh, this one is fine. It's just complaining that I'm not opening the project in a separate screen. But if I now run actually then the calculator, oh, actually, let's run go run dot. Let me redeclare them. Oh, of course, because I mixed up with build pipelines. Yeah, there we go. Let me make it a little bit bigger over here. Essentially, now that since everything is compiling and everything is working, let me actually clear the screen a little bit. Maybe even run it once again to just show it a little bit more. Right now, within the code, I am encountering this main function over here, where I'm literally created a for loop, and I'm saying, okay, just give me the next string, give me the next statement, give me the next thing that I need to be handling. And then once the next thing is coming in, then I am preparing the Lexer by giving it the input that I will input soon here below, set the position back to 0, we have no errors, and go and parse it with YYParse. So if I now say 1 plus 1, I get the result 2. If I say 6 plus 140, oh, there's my cursor. 6 plus 140, then I just get 146. So essentially, this is working. It's that simple or sort of that straightforward as long as you kind of get familiar with these steps to build already something as simple as a calculator. And I can also define a variable. So I say a equals 3. That is then being stored within the cursors. Lovely. Stored within the variables when they are being encountered. And so now then if I'm referencing it, say I do a plus 5, I get the end result 8. But this is pretty dull. I mean, it's fun, but it's not really useful. I don't guess we can monetize anymore building a calculator. Those things are long gone, unless you do something apparently, maybe do something very special with it. I would say let's build something a little bit more interesting. Let's actually build an actual language that you can do something about. So my idea is that we build a programming language as following. One that you can do a little bit more with. One that maybe looks also a little bit more familiar. One where we can define sort of functions. Say we have a print function. We can define variables using the let keyword, where we can define conditions and generate some output. To do this is again building further upon the things we just did before. Let's make then the parser.y and let's just insert the start. So this is already a little bit more complicated, but still it looks quite similar to what we've just done with the calculator. We can have the union, we have just a little bit more tokens right now, including right now tokens for the print statement, the if statement, let, etc., and very importantly, the CR, end of line character. We define a bit more tokens, so we have now less than equals, greater than equals. Just a few more iterations that you possibly could deal with and interact with. The next thing that we just want to do is we want to define our program, our block. So again, we have the begin statement, the program here on the top. But now for a change, we start again including all those different iterations, so we can have, say, a single file, say this example.tiny, say without, where we just have one print statement and one line of code. But we can also have multiple lines of code with multiple statements or expressions. Why is it opening it here? Oh, there we go. But we have to handle that. So we have to handle and indicate to the parser, hey, watch out, we can encounter the end of line as well. Right now we can also define already then, now we have the print statement, and here I'm already starting to make use of just small helper functions that I can add or that I've added, will add later here on the top of within Go, that I'm then just referencing within my parser. So I'm just saying, hey, if you encounter print, we're going to indicate back to the parser that we now encounter the operator, which is the print operator in this case. So do something with it. And again, to the similar to the calculator before, we want to have some mathematical operators that we would like to include. And the final state of the parser is when all of this again just comes together, where we have the full code blocks, all the operators, and now also all the comparison operators below. Also on the Lexer side, by the way, I just made it by hand, which is annoying from time to time. You can automate that as well. So I'm using something that, called Nex, and within Nex I can just say, hey, here are all these keywords, figure it out. I'm going to give you, like I can just give it now a bunch of strings and say like, okay, figure it out, all these tokens are here, and you just have to parse them correctly and accordingly. By the way, I have to call it right because otherwise that won't work. Lexer.nex. And then to just finish it off, let's make a compiler. Again, some Go code combining this all together, where we define that operator function and all the logic that comes below. The funny thing in this example is, so like I said in the beginning, I can build machine code for this. I can build the CPU instructions actually to do all these operators, and then in the end we'll write something back to the terminal. But what's much easier to do is just I'm writing another programming language. I'm compiling everything back to Go. So in this case, I will take this piece of code, and based on what I encounter in the compiler, I will literally just spit out again Go code that will then be interpreted or used. This is not very often the thing you want to do, but just for the sake of our time, this is by far the easiest way to go. So let's combine this all together once again. So let's go to the basic project right now. And let's see, can I clear it? Oh, it doesn't work. Better. So let's say, hey, let's build everything together, and let's see. Oh, again, because I did not prepare apparently good enough, I just have to again download those dependencies. This is not normally how you are dealing with Go, but because of that, I'm messing with my environments. I'm encountering these obscure bugs. Let's see. Oh, my parser is not working. Yeah, never do live exam real demos on stage. I did not copy and paste properly. So once again, we have then this very big Lexer file. This is then from these tokens that that I've just given. The nice thing with this Lexer file is then all these annoying situations, annoying cases that I was dealing with before by hand. This is all now done for me. And what has also been generated is actually the basic.go parser, which then parses everything together. And within the build script that I have over here, actually close all of this. I have also already here, and that's the final state, I have compiled it down to a binary executable in Go. The nice thing is now that I can just run it, go say ./basic, and I'm going to feed it the example.tiny, and some new code is being outputted, because that is the Go code that is being generated, and it is now a representation of my own language, and I can just run it. So I can say, hey, run the output, and there we go, hello world, and you shall not pass. Coming back to these slides. Yeah, I mean, it's nice and all. Maybe some of you are a little bit interested in this right now, but what are some actual real world use cases? I mentioned Docker already, but essentially the way on how you're writing Docker, or right now this really cool project Ollama, that's actually AI related, allows you to write all these definitions, all these configurations or instruction sets, depending how you look at them, to come to some state. Terraform and actually HCL are also a little bit similar. They are kind of programming languages allowing you to define your some sort of program or infrastructure based upon their specific instructions. Data retrieval, that's also a very nice use case. SQL, that's in our case very relevant. But GraphQL is also another very relevant subject. Or smart contracts. So don't know how many of you are in crypto or blockchain. Smart contracts are also kind of a form of a programming language, and also over there, it's very beneficial if you can just build a generic or a language that can then be interpreted by whatever implementation that is out there based upon a given grammar or definition. And much more. So what I want to do is I want to just give a quick sneak peek on how it actually looks like in our use case, and kind of what the benefit of it is. So let's maybe also actually show you guys the needs run open folder. It's annoying that the screen is a little bit out of out there. Yeah, it's a little bit cropped. But to give an example on how it looks like to deal with the SQL grammar. Luckily, this is done for us. I did not have to write the majority of this. This is just years and years and years of expanding the SQL definition. But essentially, this is everything what I just talked about, except then in a for a much larger project. This entire document, which I think in the end is 5,500 lines of code, defines every possible way in how you can be using SQL. And I actually snuck in here one nice keyword, Ode. With the idea that if I do select Ode, which I have defined over here, actually let me turn on support. So if I do select Ode, then I return, in our case, a tree node, which is Ode and the code, which then should result in some instruction. And if I run it over, so I've got that application, that custom binary of our product, I got it running over here. And I can interact with underlying data sources as I usually am familiar with, or I can write SQL statements with expressions like I'm usually familiar with. But if I say select now Ode, select Ode, then I'm getting now back. Of course. Then I now get back Ode and the code. And this is really the benefit of being fully in control, fully in charge of the way on how users are interacting with us. Because in our case, that really means that we can tweak our engine in such a way that we can just support a wide range of connectors and a wide range of data sources without the user having to worry or bother about this. Some honorable mentions. I really like the talk of Rob Pike, one of the Go creators, about lexical scanning and recursive descent parsing. If you just want to dive deeper into this topic, is just a really nice way on also on looking differently at lexers. If you want to reach out to me, you can find me on GitHub, on LinkedIn, posting cool projects over there and other little things and pet projects that I'm working on here and there. So feel free to follow me over there or reach out to me on my email. But thank you very much for your time. Yeah.
Yes, thanks. So for Solidity, in case of Ethereum, why would they make their own language instead of using something that's already out there, like Python or C++ or something?
I guess in their case, it is really allowing them to define a generic definition that is not relying upon the legacy of, say, Python. Python is quite an extensive language where you can do anything in. I guess the reason for why they decided to define their own contract is so that they can limit the scope of the contract and also allow the implementations of the contracts to become agnostic. So I can build an implementation of their contracts. You can do it. Anyone can do it. And since their data contract is like it's already quite an extensive contract, by the way, but or the grammar definition. But you can reproduce it. You can build a new runtime engine or a new compiler for it relatively easy. So I guess that's the main reason to why you want to do this.
Yeah, right.
Any other questions? Yeah, go ahead.
I just wondered, when Guido van Rossum was building Python, was this how he did it? Like, was this literally how he did it, or are we talking about something totally different?
He will probably have started in a similar way. He probably has made different choices about for the types of scanners, the types of parsers for Python, but essentially, yes, this is the way on how a language or like Python is being built. The steps after this in case of, for example, Python, become a lot more interesting because then we start talking about, okay, hey, we have now this abstract syntax tree and we start to try to define our behavior. Now, very often programmers define behavior or define their code in a suboptimal way, in a way that an optimizer, for example, could really improve the performance of the output, making that the code will be a lot more efficient. So those areas that you can give like another 10 lectures or whatever, like a whole computer science course about it. But yeah, essentially this is how you start with it at least. Yeah. I will be around anyhow afterwards, so feel free to reach out to me on email if you have later after this talk a question or shoot afterwards offline off stage.
Great. I do have one
No,
more
yeah,
question.
go ahead.
As I didn't understand all of it, but my first question was like, why would you do this? What would be a reason to do it? But then I also reversed it. What would be for you definitely a reason not to do something like this? When would you say, oh no, this is not a good idea?
You should definitely not do it if you want to get something done quick and dirty. I mean, you can do it with regex as well. So you can build sort of your own grammar with regex and parse it and interpret it and build something, but you will very quickly run into limitations. So it's really, if time is of the essence, then no, don't do this. It took us quite some time to get our product into a state as it is right now, where it becomes usable and where it starts to achieve the goals that we wanted to achieve.
That right now you are, I don't know how to translate this into English, plucking the fruits from the labor before, or
Yeah, for sure. Yeah.
Right.
Now we have everything is set up. So the nice thing is if all of these components start working and everything starts being there, then indeed expanding it, fixing it, optimizing it, building further starts to become easier. Yeah, that's really indeed. At this moment, we start to see our hard work to be paid off, indeed, a little bit at least.
That's great.
Yeah.
All right. Then, yeah, thank you again.
Yeah, you're
for
welcome.
your and along the way, I'm not sure if this is a thing in the Go world, but I heard you say a few times while working in the IDE, well, this is the easiest way to go. Is this actually something that you use in the, or not?
No, it's nice that you caught on to that.
Okay.
No, I don't usually say it
Okay.
or say
Okay.
that phrase that often.
Okay. All right.
It's maybe being on stage here that it's kind of my
Cool.
yeah, stopwoordje.
Go-to phrase.
Go-to phrase. Go-to phrase, exactly.
All right. Yeah, thank you.
Yeah, you're
so we'll have a short break now. Right here, the drinks are already being prepared. So we don't have to go back into darkness there where maybe the lights don't work. Go back, yes, all right. We're getting the hang of it. Yes. So after this, we have Nick talking to us about predictable, scalable, and safe terraforming, correct? So yeah, see you around and here back then in 20 minutes or something. Say 1:15. Yeah. And if Hallo. Hallo. Zullen we langzaamaan weer een beetje gaan zitten? Pak nog even wat te drinken. En dan gaan we zo meteen verder. Ik weet het niet. Waar zit hij? Zit hier nog een knopje? Oh, daar heeft iemand een afstandsbediening daar of niet? While we are getting the technology working again, I'd like to already introduce Nick, who's going to give his second talk at Ode aan de Code. Your previous talk was about pen testing. We just spoke about it a little bit. Very interesting topic. And speaking of pen testing, I just gave you a little anecdote about myself. That recently we got a call at our office, just on our main phone line, of someone requesting information about a colleague, and I was already a little bit aware, like, what is this? There's a lot of background noise. It sounded like a call center, and I said, yeah, I can ask the person to call you back on your mobile number. Just give me your mobile number, and then he will call you back. And he was like, no, I cannot. No, I don't have a mobile number. I was like, okay, you don't, okay. And he said he was calling from Utrecht, but the phone line was 010, so it was actually from Amsterdam. So a lot of alarm bells got off, and like, okay, this is a typical either like scraping data or social engineering type of thing going on. This is not social engineering. This is just Samsung engineering. But Nick will talk to us about Terraform. And does anyone remember the application Terraform from the 2000-ish era or not? Am I the only one? Okay. Yeah. So one of the earliest applications that I got into was like I was in the designing stuff, and I found this application called Terraform where you could build a landscape, like a 3D landscape. You could just render it. You could say like, I see a lot of oh yeah, I remember, I recall that. Yeah, well, that's what it is.
Kun je niet naar zo'n source thing switch of so? So last time I was here, I did this talk about pen testing, and actually I had a lot of live demos, and they all went a little bit wrong. So I thought that I would be safe now by not having live demos anymore and recording in advance. But something Murphy's Law.
But what I did see in your talk introduction, because you also had a little YouTube video,
Yeah.
and there also I saw something in the background standing on a table.
Yeah.
It was a recognizable puppet. I'm not sure whether it's a cat or... Do you remember?
Yeah.
What, yeah?
Something cat, something octopus.
Yeah, exactly.
Octocat.
How did you get it?
Order it.
Order it. Oh, okay,
Why?
it's that
Yeah.
simple. All right.
Yeah.
Okay.
Yes, I need to fix the screen, and then we'll be
Yes.
good to go.
All right. So we will have a very interesting talk about Terraform, making a predictable, scalable, and safe cloud landscape. Enjoy.
Cool. Thanks. Yes. Yeah, so as introduced, I'm going to talk about infrastructure as code using Terraform. But first, let me quickly introduce myself. I'm Nick Wortel. I'm a software consultant, trainer, and coach. I work a lot with PHP, Symfony, DevOps, Kubernetes, CI/CD, etc. And I'm also part-time working in the Dutch Army as a reservist. Something completely different, completely unrelated to my tech work, but it's actually a nice change of scenery once in a while. So I'm a squad leader there and an instructor. So that's what I do. What's the goal of this talk? I wanna just show you a quick introduction of Terraform. I heard that I think most people have not worked with it yet, so it's new to everybody. So this is not going to be a complete course, and you will be an expert in Terraform afterwards. But the goal of this talk is that you know the basics of what is infrastructure as code and what is Terraform. You understand a little bit of the workflow of how you can work with Terraform, how Terraform uses state, not the same state as in the previous talk, but different kind of state, and that you can read simple Terraform configurations. By the way, is it visible and everybody can hear me all right? All right, cool. So let's jump right in. What is infrastructure as code? The idea of infrastructure as code is that we can describe our cloud infrastructure, so any resources that we are using in the cloud, using configuration files that can be read by humans, but also by machine. This will help us to automate the provisioning and configuration of cloud resources instead of doing it all manually via some cloud console. So why would you use infrastructure as code? Well, there's a few benefits. As I already hinted, it will help you to remove manual work, which, especially if your cloud configuration becomes more complex, it will become more and more error prone. I don't know if anybody has some experience with this, but you are clicking manually through the browser, you make one wrong configuration and everything goes down. I see people shaking no, so that's good. I hope you keep it like that. But if you do recognize this situation, then maybe it can help you. Because it's code, we can also use it. We can also use version control to track the changes to our configuration. So, same as we use with any other software, we can use Git, or if you maybe you're using SVN or something else. But we can use version control to track these changes. And because it's automated, it's more reproducible. If at some point something breaks down in our infrastructure and we are in a stress situation and we need to quickly rebuild some part of it, instead of having to remember, okay, which buttons did I click exactly and what did I fill in there, we can just use our configuration, which we already have, just apply it again, and we're up and running. That also means that it becomes much more easy to create and destroy parts of our infrastructure. We can move a little bit away from this kind of service which has been running for 7 years because nobody dares to touch it, because nobody remembers how to recreate it again. But it's very easy to create a new environment or destroy one or use it temporarily for testing and then get rid of it. It's all very easy with infrastructure as code. It helps to stop configuration drift. Again, this server that has been running for 7 years and nobody really remembers what was done. Sometime it was configured, but in the meantime, a lot of manual work was done. Nobody remembers what changes were made, so we don't really know what's going on there. Again, with infrastructure as code, we have a clear definition of reality, and we can use automated tooling to make sure that reality matches the configuration, or the other way around. Yeah, and if we look at our configuration also a little bit as documentation, it actually means that we have documentation that is always up to date, because we have a clear description of what is there in our infrastructure. It's maybe not as human readable as a completely documentation written only for humans, but still we have some kind of definition of what is there. So we have some configuration or documentation which is automatically up to date. Yeah, so a few use cases that can be just used as examples of why we would use infrastructure as code. Let's say that we have a test environment that we want to keep in sync with our production environment. We all know the joke, everybody has a test environment and some people are lucky enough to have a separate production environment. But let's say we have them separated, but we want to make sure that they are in sync. And again, if we do everything manually and we have a copy with 2 environments, but we forget to apply the one change that we did in production and we forget to apply it in test as well, we no longer have a good test environment. So with infrastructure as code, we can just automate this. it also means that we can test our changes to our infrastructure before we actually apply them. So if we are going to make a big change to our infrastructure, we want to roll it out first in a test environment before we roll it out in production. We can do this again with infrastructure as code. And we can do some kind of disaster recovery automation. Let's say in 3 o'clock in the middle of the night, something breaks down. Instead of having to go manually and rebuild it, we can use, again, infrastructure as code to automate this process and to help us keep the stress levels a little bit down. Easily scale up or down. Also things like, I don't know who has ever experienced this, but I've definitely had it. I have some kind of server, I have a DNS record pointing to it, and at some point I had to replace the server, I forget to update the DNS record, and suddenly the DNS is pointing to some server that no longer exists. Again, we can automate this. Or things like, we create a managed database cluster, and we want to automatically inject the credentials to connect to this cluster into our application. This is also possible. And even things like having a GitHub organization, and we want to manage who is a member of this organization using pull requests, so that everybody can create a pull request to invite a new colleague into the GitHub repositories. And this can just be approved using a pull request. So those are just a few example use cases. So that's about infrastructure as code. Now I'm going to dive specifically into Terraform, which is the most popular tool for infrastructure as code. It's created by HashiCorp. You may know this company from some other products they have, like Vagrantbox and some other tools. The benefit of Terraform is that it has support for many cloud providers. If I remember correctly, sometime maybe a year ago or something, there was at ODA the Code also a talk about a tool specifically from AWS for infrastructure as code. So that tool only supports AWS, and in our case with Terraform, we have support for many cloud providers, so we can build a cloud infrastructure that combines AWS with Cloudflare and with some other providers. It's not a problem. As I mentioned, it's human readable and declarative configuration. Actually, Jeroen already mentioned it. HCL, HashiCorp configuration language, is the language, and I will show it later in this talk, is the language that you use to define your cloud infrastructure, and it's actually quite human readable, easy to read. It uses state to track the resources that are being managed. I will come back to that later, but basically it means that it just remembers all the things that it has created, so that later on we know what resources are created by Terraform, which makes it easier to edit them or to update them. And it is open source, or no, it's not anymore. It was open source. Recently, HashiCorp has changed the license for Terraform. I think it was like 1 or 2 months ago or something. Quite a lot of news about it. They changed from some open source license to what is called business source license. Basically, it means that most users can still use Terraform without any issue and just for free. But they changed their license because they noticed that some companies were actually competing with them with their paid product, and they were using the open source version of Terraform to compete with HashiCorp, which is technically should be possible with open source, but yeah, apparently it was hurting their business and they decided to change the license, which is a little bit unfortunate if you are a fan of open source like I am. As a reaction to this, a few of those competitors of HashiCorp created their own fork of Terraform, which is called OpenTofu, and which is actually became part of the Linux Foundation now. So basically they forked the last version of Terraform that was still open source, and now they're trying to stay up to date with all the new features of Terraform. I don't think a lot of companies are switching yet because, as I said, most companies, it doesn't really bother them because under the terms of the new license, they're still just allowed to use Terraform for free. So I'm still looking at this with a little bit of mixed feelings, but we will see how it goes. For now, I'm personally just staying with Terraform, and I think most companies are, but let's see how it develops. Before I dive deeper into Terraform, I want to quickly mention a few other tools that are alternatives to Terraform. One is called Pulumi. Anybody heard of it? Cool. So Pulumi is actually, I haven't really used it myself, but it's basically a tool that you can use to write your configuration in any of a few languages. So for instance, PHP, JavaScript, and some other languages you can use to define your resources. And then Pulumi will do, will basically do the same as Terraform. Then we have some cloud-specific tools, like I mentioned. AWS has CloudFormation, Azure has Azure Resource Manager, Google Cloud has Deployment Manager. So those are cloud-specific tools. And then we have some other tools like Ansible, which are not specifically infrastructure as code tools, but you can also do similar tasks with them. Yeah, but this talk, I'm going to focus on Terraform. I just wanted to show the alternatives. So I'm going to do some demos. As I mentioned, last time I was here was half a year ago. I did a talk with a lot of demos that went wrong. So I learned my lesson. I recorded them, so it's a little bit more boring than having the guts to do it live, but still. So I'm going to show a few demonstrations to show some basic capabilities of Terraform. So we're going to start with a simple project. I'm going to use AWS, where I want to start a simple EC2 instance, a virtual machine of Amazon, which can be for any reason. Let's say that we have created our own compiler and we built our own program and we want to run it in the cloud. So before I dive in, I want to quickly show what is called providers. So providers are a concept in Terraform, which are basically plugins that plug into a specific cloud provider. So there's a big bunch of providers available. Some of them are created by HashiCorp itself. Some are created by cloud providers, and others are just created by people from the community. You can find them all in a registry. So Terraform has its own registry where you can search for these providers and search for one that will help you to plug into your cloud provider. So a few examples: AWS, Azure, the common cloud providers, Cloudflare. You can also use it for things like Kubernetes and Helm, but also for things like GitHub, GitLab, and some monitoring and login tools, authentication tools, etc., etc. So a lot of different things that you can manage with Terraform. So let's dive into the code. And this is first example. This is the HashiCorp configuration language. So this is how you can write configurations in Terraform. So the first thing that we need to do is, because I want to spin up a service on AWS, is I need to have the AWS provider. And as you can see, this one is actually provided by HashiCorp. So it's in the HashiCorp namespace. And in this case, I specify that I need at least version 4.16. So before I can continue, first what I need to do is I need to run one command on the command line, which is Terraform init, which will basically, based on this configuration, it will install the required version of the provider for me. Yeah, so that's it. Now, next step is that I can actually start using this provider, and I need to configure it first. So in order to communicate with AWS, I need, of course, to have some kind of authentication. So I have to specify an AWS access and a secret key. So I go to my AWS account, my console, I create this key pair, and then I can configure them in my Terraform configuration. So first I create a variable that can hold the access key. I do the same for the secret key. And then I can actually configure the provider where I pass a region and the two keys. Now the next thing is that in a separate file, which of course I want to have in my git ignore because I don't want to commit this kind of credentials, I will store the actual values of the two variables. Alternatively, if I want, I can also use environment variables. Depends a little bit what is your preference. But either way, we want to make sure that it's not being tracked in Git. Then comes the actual magic. As I said, we want to spin up a AWS EC2 instance. So we're going to define that as a resource in our Terraform configuration. So I start the line with a resource, because we're going to define a resource. I need to define what kind of resource, in this case, AWS_instance. And then I just give some name to it, which is any arbitrary name that I can choose. In this case, I choose to call it VM, but that's whatever kind of name you want to give it. Any kind of resource requires some kind of parameters, which depend on the kind of resource that you want to define. In this case, because we're going to spin up an AWS EC2 instance, I need to provide a Amazon machine image, which is seemingly some kind of random string, but it defines what kind of image we're going to use for the machine. I'm going to define the instance type, so is it really expensive big machine or just a micro instance like this? And I can define some tags. In this case, I'm going to give it the name demo instance. Now the next step is that I can run Terraform plan, which is a command which will basically let Terraform calculate, okay, what kind of changes do I need to make in order to reach the configured configuration, the state that we want to be in. So Terraform will make this calculation. Unfortunately, because it's a recording, I cannot scroll up, but basically it just shows, okay, I'm going to create an EC2 instance with a lot of variables. Some of them will only, or yeah, most of them will only be known after the instance is actually created. So this is the plan. One thing to create and nothing else. So I can check this plan, and if I'm sure, like, okay, this is what I want to do, the next step is that I'm going to run Terraform apply. Now actually, because I didn't save the plan and then pointed the apply command to the plan, it will again create a plan, and just to be checking, and then it asks, okay, are you sure you want to perform this? I say yes, and then it starts creating the AWS instance via the API of Amazon. This will take a few seconds. Benefit of the recording is that we can speed it up. And after that it says, okay, apply complete. I created one instance, and I'm done. So now I've just created this screenshot to show that indeed in the AWS console we can see that the demo instance has been created. I don't know if it's visible from the back because maybe it's a little bit small, but we see the name is demo instance, we see that it's running, we see the instance type is t2.micro, etc. Yeah, so that's basically a very quick example or demonstration of how we can create a simple EC2 instance using Terraform. Now the nice thing is that of course we're not just going to create our infrastructure once and then never going to change it again. So of course we want to also be able to change things. So that's the next thing I'm going to show. Before I dive deeper into that, I want to quickly discuss again the state that I mentioned in the beginning. So what Terraform does is that whenever it creates a new resource or starts to manage a new resource, it will store it in its own state. And this way, Terraform will always know which of the resources it is managing, and in that way it can track changes and make sure, so if you change your configuration, it will know that it has to change something. If you remove some part of your configuration, it knows that it has to clean up some things. I don't know if anybody has some experience with Ansible, for example. So Ansible or familiar tools, at least I know from Ansible, it doesn't work with state. So with Ansible, you can create a configuration. I want a certain file to be on my machine or something like this. It will do so. But then if I remove this configuration, Ansible will not automatically remove this file from your machine. So things will stay there, even though it was removed from your configuration. By keeping track of state and by keeping track of all the resources that it has created, Terraform knows exactly, okay, if I don't see it in the configuration file anymore, it means it needs to be removed. So I will remove it from the cloud infrastructure. So let's make a small change to the definition of our instance. So what we had before is this one random string, which actually was for Ubuntu 20.04 LTS. And we want to upgrade our machine to a newer version of Ubuntu. So we're going to upgrade to 22.04. So I'm changing this string, this variable AMI. I made actually a screenshot of this because in the recording I'm not able to scroll back, but you will see if I run Terraform plan now, it will say the Terraform has computed what actions it has to do, and it will notice that it has to replace the EC2 instance. Because if we're going to change the machine image, we cannot just change the image of an existing machine, so we need to destroy the machine and create a new one based on the new image. So it has already calculated that it has to do this replacement. So now if I run Terraform apply, I will again have to, it will again make the plan, it will ask for confirmation. I type in yes. And you see it starts to destroy the old machine. Again, this takes a little bit of time. Luckily, we can speed it up a little bit due to the recording. Explosions everywhere at the AWS data center. Destruction complete after 30 seconds, and now it starts to create a new one. Cool, apply complete. One resource has been added and one has been destroyed. Now you may point out that, of course, this is fine for some test environment or whatever, but if this is a production environment, of course, we don't want to create first the old machine, and then we have some downtime for all our visitors because no machine is up and running until the new one is ready. So in a production environment, we probably want to do it the other way around. We first want to create a new instance, and then when it's up and running, we destroy the old one. So luckily, this is possible in Terraform. It's actually quite simple. We can use the lifecycle meta argument. So basically, we add some configuration to our resource saying, hey, if you are going to replace this, I want you to first create a new version before you destroy the old one. So let's do the same thing, but with this new configuration in place. So now we see that first it starts to create the new instance. Again, it will take like roughly 30 seconds. Who guessed 32? Yeah, now the new one is up and running, and now it starts destroying the old one. Of course, I'm not taking into account things like, okay, we have a new machine, but we still need to install the software and blah, 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 blah. It's just to demonstrate the fact that you can change this order of creating an instruction. Yeah, so this is a quick demo of updating an existing resource, in this case by replacing it because we cannot change the image of an existing machine. Let's say it's not our production environment, but it's some kind of temporary test environment, and we just want to destroy the whole environment or part of it. Well, guess it or not, the command is Terraform destroy. It will, of course, first ask for confirmation. Luckily. You really want to destroy all resources? Yes. Okay, let's do it. Yeah, so this makes it really simple, not just to not only to manage your production environment, but also short-living test environments or demo environments or whatever. If you're worrying like, okay, what if I accidentally destroy production? Actually, you can use the same lifecycle arguments. Also, there's some option to prevent destruction, so you can say, okay, never allowed to destroy the production environment. Or what I do personally, for instance, I have some Kubernetes cluster which is stateless, so it's quite easy to replace. But for actually my database cluster, I have this prevent destruction, so I never accidentally destroy my database. Yeah, so we talked about resource. The next thing I want to show is a data source. a data source is basically a way that you can have Terraform query some data from an existing resource that is not being managed by Terraform, or that is being managed somewhere else in a different Terraform configuration. In this case, we saw that when I had defined the EC2 instance, that I had this quite random string, which was the Amazon machine image. So instead of this random string, I actually want to make it easier to find this random string by querying the AWS API and by looking up for a specific version of Ubuntu. So what I'm going to do is I'm going to define this data source, and instead of resource, it starts with the word data. I again have to specify what kind of thing I'm going to query. So in this case, an AWS_AMI. And I again give it my own arbitrary name, which is Ubuntu in this case. I specify that it has to be the most recent version within the version constraint. It needs to be owned by Amazon. And I filter on a name which should start with Ubuntu images, etc., etc., etc. Yeah, so we search in this case for Ubuntu 22.04. Now that I have defined this data source, I can just refer to it in the resource that we defined earlier. So this is again the resource that we had. I'm just going to replace the random string of AMI with a reference to data.awsami.ubuntu, and then I'm going to grab the ID of that data source. I could run Terraform plan and apply now, but actually nothing has changed because this data source will just give me back the same Amazon machine image ID that I used before. So nothing is going to change. It just makes it more maintainable and more easy to read. Next thing I want to point out is dependencies between resources. Because up until now it has been quite simple, just one simple EC2 instance. But of course, in reality, we're going to have a more complex cloud environment where we have multiple different resources that point to each other or connect to each other, etc. So what I'm going to show is I'm going to keep the example of the EC2 instance, but I'm going to use Cloudflare to actually have a DNS record that points to this machine. So first, of course, we are going to need to define the version and the name of the new provider. So I'm going to add it to my required providers block, Cloudflare, version 3.0 or higher. I again have to run Terraform init. Cool. And again, I need to specify, I need to define a variable that will hold the authentication token. So I have an API token, and I will initialize the provider with that API token. Okay, now I'm going to actually update the rest of the configuration. So we have already the existing AWS instance resource. I'm going to add a data source for the Cloudflare zone, because I actually already have this Cloudflare zone defined in another configuration. So I'm just going to query it because I need its ID. And I'm going to define the resource, which is the Cloudflare record, the DNS record that will point to the EC2 instance. Yeah, so it has the record resource has a zone ID that refers to the data source. And we have a value, which is the actual value of the DNS record, which is the IP address, the public IP address of the AWS instance. So this way, I connect my DNS record to the instance in order to make sure that we have the correct IP address. Going to run Terraform apply again. Yeah, it mentions that it will create the record. And everything is up and running. Well, this is not so interesting yet, of course, but remember what I mentioned in the beginning of my talk. I've definitely had this myself. I have some instance running, I have the DNS pointing to it, then at some point I need to upgrade the instance, I replace it, but I forget to update the DNS record. And everybody, the site is down and nobody can reach it anymore. So that's actually where it becomes interesting. Let's say that we want to that we're going to replace again the EC2 instance, and we want the DNS record to be automatically updated to point to the new IP address. Luckily, we have the data source, so now instead of looking up some random machine image ID, I just changed the filter for the name. So we're going to downgrade again to Ubuntu 20.04. And I'm going to run Terraform apply again. Yeah, so it will replace the instance, but it will also notice that the DNS record will be updated in place. Yeah, so the record can continue to exist, we just need to update its value. Because we still have the create before destroy argument from the first step, it will first start to create this new machine. Then it will update the DNS record, and then it will destroy the old machine. Cool, and it's done. Okay, of course, again, for real production environments, of course, we have to deal with things like DNS caching and that kind of stuff. Let's just imagine that we are using the Cloudflare proxy, so it's instant switch to the new IP address. But the idea is that instead of having these implicit connections between different things that we just do manually, now with Terraform, we can make these dependencies explicit. So we can make these relations between different resources explicit, and they will automatically be updated if they need to be. And in my experience, that's really a big benefit of using infrastructure as code. Next thing I want to quickly mention is modules. And modules are a way in Terraform to organize your configuration. Because as you can imagine, this is still a relatively simple example with just an instance and a DNS record. But in a real production cloud infrastructure, you will have much more complicated configurations. And just as with regular code, it's really useful to be able to structure it a little bit, to encapsulate some things so that we can make it more easily maintainable. Yeah, so modules allow us to organize our code, reuse pieces of configuration. Let's say that we need to reuse a bit of configuration to create a certain instance, that we can just put it in a module and we can call that module a few times. And it helps with encapsulation. Now, one thing to point out is that actually always when you use Terraform, you always have at least one module, because actually the root module, where we were working in before, is also considered a module. So we always have one module, but if we have more complex configurations, we can actually break it down into multiple modules to make it more maintainable. So let's say that we have a module, for instance, to configure a database cluster. And in this case, I put it in a subdirectory called modules, and then again a subdirectory called database. So in my main configuration, in my root module, I can just refer to that module by using the module block, giving it an arbitrary name again, and then pointing to the source where it can be found. And this can be locally in the file system, it can be some module that is found again in the Terraform registry, it can be a Git repository, etc., etc. Yeah, so this is how we define the source. In this case, again, as I said, the local directory. And I can also specify a few input variables. So let's say that I want to make multiple databases with different names. By specifying the input variable, I can specify, okay, this one has to be called demo, and another one has to be called yada, 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 etc. Also really useful is modules can also return some information by using outputs. So we can define, in our module, we can define pieces of information that we will send back to the place where it was being called. And then in the root module, we can again use this information. So in this example, let's say we have this module to create a database, and the module will give back the credentials to connect to that database. And that way, in our application machine, we can actually inject these credentials into the application so that it can actually connect with the database. And again, we're using explicit connections instead of implicitly putting the database password in some variable in the application. And if we forget to update it when we change the database password, everything will break. So again, this explicitness, these explicit dependencies are really helpful to keep your stuff up to date and to prevent issues. This is what I already mentioned. We always have one module, which is the root module, and from the root module, we can actually call other modules as well. So I'm going to do a recap because I can go on for hours, but we don't have so much time. So I quickly want to repeat what we have gone through. So we've discussed what is infrastructure as code, what is Terraform specifically, and I showed a few examples for building some simple infrastructure, using providers to connect with different cloud providers, making changes to our existing infrastructure, using the state, also destroying infrastructure, how we can use data sources to query information about things that are not being managed by Terraform, how we can use dependencies to create relationships between different resources, and how we can use modules to organize our configuration. So as I mentioned, I don't have the time to go all in depth and discuss everything about Terraform, but if you feel like, okay, this is definitely interesting for me, I want to use this at my organization, but I don't know where to start, the first thing I can really recommend is the official documentation of Terraform itself, because they have quite a good website with documentation, but also with tutorials, which will really help you starting from the basics and go into the way more specific stuff. Also something I've been working on myself, not just for Terraform, but for quite a number of tools. First of all, for myself, I just wanted to create some cheat sheets for myself to store some information which I all the time was looking up. So now I have just a cheat sheet for myself to have it next to my computer and to quickly find something. So if you want to check it out, it's also for some other tools like Docker and Kubernetes and Git, etc. Check out my website. You can download them for free. And if you want to look it up, here's a QR code that you can scan to find the same thing. And that's about it. Is there any questions about what I mentioned? Yeah.
Hi, love the talk. I was just wondering, how do you manage state? If I run Terraform on my laptop, it probably will build up the state on my laptop. If you run it, do you have to use a central host, or are there more better ways to do so?
Yeah, good question. I didn't really dive into it during the talk, but indeed, when I just run it locally, and I'm the only person working with it, the default way that Terraform will deal with it is just to store it in some files that are on your machine. But as you mentioned, and as you can imagine, if you're working together in a team, that's not going to work. Because these are not really the type of files that you want to commit to Git. Actually, you shouldn't, because they can also contain some secret information. So instead, you want to store it in a central place so that you can collaborate with each other and you can all share the same state. You can do it in a few different ways. Of course, you can use the paid Terraform product, the Terraform Cloud, which is one way to do it. But it's also possible to just store it as a file in some kind of S3 bucket or some other storage option. I don't know the whole list from the top of my head, but there's definitely a few different options how you can store the state in a central place and lock it down so that only the people have access to it that are supposed to have access to it. Does that answer the question? Cool. Okay.
Any more questions? Something popping up? Yeah.
Did you already try to implement it into your continuous deployment instead of running it locally on your machine?
Personally, for my own projects, I just run it locally up until now. It's still one of the things on my to-do list. But I worked with a client who actually did that. So they had GitHub Actions running. They had the repository with their central Terraform configuration. And for any change that we wanted to introduce, we had to create a pull request, and they had some automations running so that the pull request will show the output of the plan. so that we can actually see in the GitHub pull request, okay, what is going to change, what are going to be effects of this change. And then if it would be accepted and the pull request was merged, it would again automatically trigger the GitHub actions in order to actually apply the changes. So in that way, we had indeed continuous integration and continuous deployment, basically. Yeah.
There was another question.
Hello. Yes.
Hello.
I was wondering, is there a way to run this locally? Like you're trying this out with AWS, for instance, or Azure.
Mhm.
Is there a way to sandbox this, for instance, if you want to learn stuff? Or
Yeah, sure. So actually, I didn't mention it. I think the micro instance of AWS is actually, there's some kind of free plan, so you can do it even that way. But you can also do if you just don't want to do anything with the actual cloud. Yeah, as I mentioned, it also has providers for Docker and Kubernetes and this kind of tools. To be honest, and I didn't really dive into this because it's a whole other thing that we can have a whole other talk about. It's not really the best match to use Terraform in order to manage your running Docker containers, in my opinion. But if you just want to try out Terraform without any cloud dependencies, then you can definitely use it that way. I think it's even one of the tutorials on the Terraform website.
Okay, thanks.
Any more questions popping up? I do have one more question.
Go ahead.
When it comes to auto-completion and stuff when writing these Terraform files, is it YAML or is it
No, let me get.
is it Terraform specific language? I was just wondering, is there any like extensions for your IDE that you recommend to?
Yeah. I use Visual Studio Code. As I remember, I just have some kind of extension for Terraform running in there. I also, because I have a PHP background, I also use a lot of PHP Storm, and they also have a plugin for it. So that's definitely working. And you mentioned it before, I actually used also GitHub Copilot, and it's also actually quite good in picking up my intention and suggesting some auto-completions. Yeah.
Okay, thank you. Nothing else? All right. Then a round of applause for Nick.
Thank you. I have actually one last request myself, because I actually created a small feedback form. So if you have some time, you would really help me out to scan the code and to answer the questions, and it will help me to improve my skills for the next talk I'm going to give. So thanks very much in advance.
All right. Well, everybody is providing some feedback. Excellent idea, by the way. I think that really helps. So we have some drinks.
No, it's I promise. Believe me on my blue eyes.
So I'd like to thank everybody for their attendance. Special thanks to the speakers. Can I invite you to the front as well for a short thank you again. My lieftallige assistant, Ruben. Yeah.
Oh, thanks very much. That's going to be lovely.
Small token of appreciation for
Yes.
your great insights again. We hope to see some talks about your topics soon again. We don't have an Ode on the Code planned yet, but there will probably be one in February. So just keep a close eye to our meetup page. You're probably all subscribed because I see a lot of familiar faces. But tell your friends, tell your colleagues that we have great talks. So thanks again, everybody, for joining in. There's still plenty of time for drinks. There are still plenty of drinks left as well, and snacks and everything. So feel free to stay for a bit more and talk and chat. We hope to see you all again the next time. Thank you.
Awesome.